Record.
Cool.
And all right, recording.
Great.
All right.
Well, welcome everybody. Welcome to the zkStudyClub. Today we have Alin Tomescu, who's going to be presenting his work on authenticated dictionaries and cross-incremental proof aggregation and disaggregation. I think I got that right. For this organization, I want to say thanks to Alex for helping put this together. Alex, maybe just put your hand up, say hi real quick.
Hey, Alex, face to the new name on Telegram.
Yes. So Alex is actually going to be working a little bit more with me to do the zkStudyClub. Hopefully we get to do this more regularly. I'm very excited to have him helping out, and you're going to be working, I guess you'll be fielding some of the questions on this edition. Yep. One thing before we start, I just want to remind everybody that the ZK Summit is happening on November 23rd and 24th. So put that in your calendar. I will be sharing more info soon, but I just want to make sure everyone here knows about it. Yeah. Cool. Okay. So I think we should kick it off.
All right. So I guess I'll take over from here. Thanks, Anna, for having me again. I feel quite honored. This is like almost like a peer review for my e-prints, you know. I just discuss them in the zkStudyClub and I get all this great feedback. So I really appreciate it. So today I want to tell you all about our new work on authenticated dictionaries with the notion of cross-incremental proof disaggregation and aggregation. And this is joint work with my MIT lab mates, Yu Xia and Zach Newman. Well, I should say ex-MIT lab mates, but we've continued to work together. And let's get started. So the motivation for the work is to figure out a way to do more efficient stateless validation and also other applications. So specifically, we want more powerful authenticated dictionaries for authenticating validation state, which takes hundreds of gigabytes in cryptocurrencies like Ethereum and impedes scalability and decentralization. And you could say, well, just use a Merkle tree, but previous authenticated data structures from Merkle trees or other techniques are not actually sufficiently updatable, aggregatable, or sufficiently efficient for this task. And there is some previous work that shows vector commitments actually suffice to authenticate the validation state. But because vector commitments are much smaller, they limit the smart contract memory. And as a second application, we want to build transparency logs. So some of you might be familiar with this project called Certificate Transparency that actually secures the web every time you go and visit any HTTPS website. So these transparency logs are really just append-only authenticated dictionaries that map each website's domain name to the list of their public keys over time, so that websites can audit their public keys. And so sort of previous work either builds these things from Merkle trees, which requires extra trust assumptions to keep the logs append-only, or there's some other previous work that uses RSA and bilinear accumulators, but has kind of super high overheads. And I should know because this is my work and I implemented this stuff and it's super slow. And finally, I think we want authenticated dictionaries for their own sake. I think non-Merkle authenticated dictionaries are interesting and are more powerful. And that sort of finishes the motivation for this work. So our contributions are this new notion of cross-incremental proof disaggregation for authenticated data structures. So the idea is that I have a bunch of different authenticated dictionaries, D1 through DN, and I have a proof with respect to each digest DI. And now I would like to be able to aggregate these proofs with respect to these different digests into a single succinct proof. And this is a notion that was originally introduced by point proofs by Gorbunov et al. And here we generalize it so you could do it incrementally, in the sense that after you've done this cross aggregation once with respect to a bunch of different digests, if you get some other proofs with respect to some other digests, then you can sort of incrementally aggregate those into the previous cross aggregated proof. And not only that, you can take a cross aggregated proof and disaggregate it into its components. So if that doesn't make sense, please feel free to ask questions now. And in general, by the way, I would love to get questions live, so feel free to interrupt. It would be great to have a back and forth. And another contribution is we actually construct an updatable authenticated dictionary that supports this notion and can be used for stateless validation. And we also give a new append-only authenticated dictionary that's more efficient and I want to say more versatile than previous work and can be used for transparency logs. And in this process, we also give some new techniques to compute non-membership witnesses, all of the witnesses across different but related RSA accumulators. And we also give techniques for aggregating such witnesses. And finally, we give a faster algorithm for extracting witnesses in Bonnet et al.'s proof of knowledge of co-prime roots, or POKCR protocol, which lies at the core of our cross-incremental proof disaggregation. Okay, so let me sort of paint a picture of how what the capabilities previous authenticated dictionaries have and what we bring to the table. So kind of ignore these footnotes here because I didn't know how to animate Beamer properly to make them appear at the right time, but they'll make sense in a second. So we have the popular Merkle trees. Merkle trees do not support any type of proof aggregation, not even if I have a bunch of proofs with respect to a single digest, I cannot aggregate them, at least not efficiently. In principle, I can do it if I use snarks, for example. They have a notion of security. This is the binding notion of security that is strong in the sense that if I have an adversary that outputs, an adversary cannot output a digest that says different things about a key's value. So it cannot say that this key has value VK and VK prime that are not equal. So that's called strong binding. And the adversary is allowed to output this digest adversarially. That's where the strength comes from. It's a very strong adversary. And Merkle trees are updatable in the sense that if I have an individual proof, that's where this I stands for. By the way, can people see my cursor if I move the cursor? Yeah, okay, because I'm gonna be doing that a lot. So Merkle proofs are updatable, but in order to update a Merkle proof, let's say for position I after position J changed, I need an update hint. I need some auxiliary information to do this update. So if I want to update the proof for I, well, I actually need the proof for J too, if J changed, in order to update I. So this is what we call an update hint, and a scheme is called update hint free if it doesn't require any such information, and you can just do the update directly. Merkle trees are not like that. And if you organize the Merkle tree properly, you can get non-membership proofs. So imagine a prefix Merkle tree or a binary search tree that's Merkleized and so on. Unfortunately, if you organize the Merkle tree for non-membership proofs, you lose the ability to prove append only. And this is actually an open problem to support both things efficiently in a Merkle tree. You can also organize the Merkle tree to support append-only proofs, but then you lose non-membership proofs. So I suspect you cannot do this efficiently in Merkle trees, but I don't have a proof that you cannot. So it'd be really cool as future work to come up with that. And finally, in a Merkle tree, it's very easy to compute all Merkle proofs fast because you just Merkleize your data, you get the tree, and you have all proofs. So I hope sort of these columns make sense as to what I'm describing here, and then I'm going to go through some other schemes, including ours. There's some really cool work from Eurocrypt 13 by Papamantu on building streaming authenticated data structures from lattice-based hash functions. And this is basically just like a Merkle tree, but it's a little bit cooler in the sense that you can also update the digests, not just the proofs. And it's update hint free. You don't need any information to do these updates, any auxiliary information. You have a proof for I, J changed, you can just update the proof for I, you can just update the digest. Whereas in Merkle tree, if you want to update the digest, you need the update hint. And actually, I should have had a D here in updatability for Merkle trees. The digest is also updatable in the Merkle tree, but you need the proofs for the things that changed. It's a slight error. Finally, also by Papamantu et al., there are authenticated hash tables. These only are secure under weak binding, which means if you have a correctly produced digest, not adversarially produced digest, the adversary cannot equivocate about the value of a key. But the assumption here is that the digest was produced correctly. And these weak binding authenticated data structures are actually all you need in the stateless validation setting, because in that setting, the digest is always produced after appending a bunch of blocks to the blockchain, and these appends are verified by the miner, and the authenticated data structure digest is produced correctly after those appends. And unfortunately,
so is this the difference between a collision property where the adversary is trying to produce two data structures, and kind of a second preimage property where they're trying to produce another structure that matches the same hash that they're given?
I actually really love that question. I've never thought about it in that way before. I will say that strong binding usually implies collision resistance. I remember working this out for myself earlier on. I don't know if weak binding does though, and I'd have to think about that for a second. Maybe we can discuss at the end. That would be interesting to figure out.
Okay.
Yeah. Okay, so authenticated hash tables are not updatable, unfortunately, in the sense that you cannot update the digest, you cannot update the proofs efficiently. And in that sense, there's no sense in talking about update hints. They do support non-membership proofs, they don't support append-only proofs, and they can be pre-computed fast. There's really cool work by Bonnet, Boons, and Fish on building key value commitments. Again, another name for authenticated data structure. And I think this was the first construction that actually supported one-hop proof aggregation, which means I have a bunch of proofs with respect to a single digest. I can aggregate these into a single proof, and that's all I can do. I cannot take some other aggregated proof and continue the aggregation incrementally. I can just do it one hop. And they are also updatable given update hints consisting of the proofs for the changed positions. They support non-membership, they don't support append-only, and you can pre-compute all proofs fast. And Bonnet et al. Also give a faster version of their first construction, which is only secure under weak binding and can be used for stateless validation and has the same features as the first one, but saves like an order of lambda work concretely, where lambda is a security parameter. Yeah.
Can you just clarify what fast means in the last column?
Good. So I want to compute n proofs, and I want to do it faster than n squared. So I usually want quasi-linear, n log kn time.
Okay, thanks.
Yeah. Then there's the authenticated, append-only authenticated dictionary work, which doesn't support proof aggregation, has strong binding, is not updatable, supports non-membership and append-only proofs at the same time. And as far as we know, this is the first construction that supports this. So both proofs are logarithmic sized if you use RSA accumulators. And it supports a way to pre-compute all proofs fast, but the construction is de-amortized and is very inefficient.
Is it specifically RSA, or is it any group of unknown order?
It's, I think, well, to the extent that you could build RSA accumulators over groups of unknown order, it's any group of unknown order.
Okay.
But there was some recent troubling ePrint on breaking class groups, which I haven't really spent the time to understand.
Yeah, it was one specific property that some protocols relied on. I can't remember which one. The low order assumption.
The low order, right? But I couldn't understand if there was a way to check if a hidden order group actually was, if a class group actually was susceptible to that attack, or if you could trapdoor a class group so you couldn't tell if it's susceptible.
Yeah, I think it was mainly about constructing trapdoored parameters.
Well, then that kind of kills pokey proofs for a bunch of accumulators in those groups. Okay. Then there's some work by Leung et al. On building, again, authenticated dictionaries from vector commitments as a building block. And they use the point proof vector commitment. And they support the aggregation of proofs, but it's only one hop. They're secure under weak binding. And this is kind of inherent to their construction as far as I can tell. They cannot be made strong binding. And they do support updating digests and individual proofs as long as you have some update hints, which are static actually. They don't consist of proofs for the changed positions. They just consist of some static information associated with each position. And they have non-membership, no append-only, and actually no way to pre-compute proofs fast as far as I can tell. Maybe there's a way to do that, but I couldn't trivially build such a way. Finally, concurrent with our work, there's this really cool paper by Shashank Agrawal and Srini Raguraman on also building authenticated dictionaries from vector commitments, from Catalano-Fiore vector commitments, which is what we use as well. So they support one-hop proof aggregation. They are secure under weak binding. However, I suspect this is not inherent. They could actually get a security proof for strong binding too. They support updating digests and individual proofs, and they don't need update hints. So this is really, really cool that they don't need update hints. And unfortunately, they do not explore building non-membership proofs. Again, I don't think this is inherent. I think their construction could be changed to support that. They don't support append-only proofs. Perhaps that could be done too. I haven't investigated. And they don't have a way to prove everything fast. Again, I don't know if that could be supported. And finally, we have our first construction, which is an updatable authenticated dictionary, which supports the stronger notion of aggregation, of cross-aggregation that can be repeated incrementally and can be disaggregated back into its components. Our construction is inherently weak binding secure, which means it's only usable for stateless validation and applications like that. But it's highly updatable in the sense that you can update aggregated proofs, you can update digests, you can update individual proofs, and you can also update cross-aggregated proofs. And it's not update hint free in the sense that you need some auxiliary information to do these updates. So it'd be really nice to sort of integrate the changes from KVAC into our construction and get update hint freeness. But unfortunately, I think that would break a lot of the other properties we have. Then we also support non-membership proofs. However, these non-membership proofs can only be one-hop aggregated. Fortunately, in the stateless validation setting, I don't think there's actually a big use case for non-membership proofs. That remains to be seen. And we support append-only proofs and computing all proofs fast. And finally, we take this UAD and we add strong binding to it. And as a result of adding strong binding, we kind of lose the cross-incrementality. We only get one-hop aggregation. We still maintain some updatability of aggregated proofs in the sense that we can update aggregated proofs as long as an existing key in the dictionary has changed. But if I add a new key or remove a key from the dictionary, I cannot update cross-aggregated proofs. I'll maybe touch upon why that's the case towards the end of the talk. And once again, we need some auxiliary info to do these updates, and we support non-membership, append-only, and efficient proof pre-computation. Okay, so I really wanted to spend a lot of time on contextualizing the work because I think this is a part of the presentation that it's easier to understand than the math that's gonna come up. And I also want to say that I made an effort to reduce the math, and my collaborators helped me yesterday to get rid of a lot of it. So I hope the presentation is not too mathematical. So that being said,
I missed what ADIX meant.
Yes, good. So ADIX is just what the updatability of the construction is. So the big A stands for aggregatable proofs are updatable. The D stands for digests are updatable. I stands for individual proofs are updatable. X stands for cross-aggregated proofs are updatable. Does that make sense?
Yes, thank you.
Okay, great. Okay, so the rest of the talk will kind of be background on the building block of our construction, which is the beautiful vector commitment by Catalano-Fiore. And then I'll present how we build our UAD, our updatable authenticated dictionary. And then I'll touch upon what we do for our AAD without going into too many details. And then I'll conclude. And I obviously advise you to read the paper for more details. Here, I'm just trying to give a lot of intuition and explain some things that don't really actually, we don't actually explain in the paper. So I hope this will nicely complement that. Okay, so let's begin with the CF vector commitment scheme, originally by Catalano-Fiore and extended by Lion Malavolta and Campanelli et al. And here I'm really describing CF after these extensions. So keep that in mind. This is not the original CF, it's kind of the extended one. So assume I have a vector V with elements V1 through Vn. And while you assume that, I'm going to pour some coffee. And its digest, which I denote by digest of V, or its commitment, is just two things. The first thing is an RSA accumulator over all of the positions J in the vector. And how do I build that accumulator? I take each position J, I hash it to a prime EJ, and I do the product of all prime in the exponent of this generator G of a hidden order group. By the way, everything in this talk is hidden order groups, RSA groups or class groups if they're still usable. The second part of the digest is this lambda component. And what this lambda component is, it's really a multi-exponentiation of the RSA witness for position J raised to the value at that index, right? So S to the 1 over EJ is an RSA membership witness for position J with respect to the accumulator S, if you guys recall that. If not, you can just look at it as S to the 1 over EJ. It is useful to realize that this is an RSA accumulator and this is just a membership witness with respect to the RSA accumulator. And that's kind of it. It's just these two group elements. If you want to update this digest after position J changed by delta J, you must have this auxiliary information called an update key, consisting of this non-membership witness for J. And the way you do the update is very easy. You just take this lambda and you sort of changed Vj by adding in this s to the 1 over ej raised to the delta j, which will change Vj here in the exponent. And a few critical observations: the values Vi have to be L-bit numbers, and the primes EI have to be L+1 bit numbers. And as far as I can tell, this is really strict. They have to be strictly greater than L+1 bits for security to hold. If they're not, then you cannot really prove security, as far as I can tell.
Delta J is the new value minus the old value, is that right?
Yes, yes, yes.
Okay.
Yes, thank you. Thank you for clarifying. And one thing you might wonder is, well, when I commit to this vector, it's easy to compute S in linear time, but what about delta? Because I have all of these different roots of S. I have an ejth root of S, and I need this root for all of the possible different J. And it turns out I can compute all of these roots of J using a classic algorithm originally proposed by Sander et al. And recently renamed by Bonnet, Boons, and Fish to root factor, which I think is a really good name. And root factor basically takes the generator G and all of these things in the exponent of G, E1 through En, and gives you all of the roots of S, E1, E2, En. And so notice that G to all of this is S, and root factor gives you G to all of this but one thing in it. And it gives you that for all of these one things. And this is a really cool algorithm that's very useful for the CF scheme. So Campanelli et al. Leverage it a lot to speed up their construction, and we also leverage it in our paper a lot. So if this doesn't make sense, now would be a good time to ask a question about it. And finally, like I said before, S is an RSA accumulator, and S to the 1 over EJ is just a membership witness with respect to that accumulator. Okay, how do you prove things in CFVC? So suppose I actually want to prove that a bunch of positions I in a big set, capital I, have values V sub I. So I'm generalizing the notion of a proof. I'm going directly to the so-called subvector proofs rather than going through individual proofs. And actually, this is kind of what's the beauty about Catalano-Fiore VCs, is that you can look at a proof pi I for I as just the digest of V without positions I in it. So I'm denoting this by V minus VI. I'm kind of defining my own notation here. And if you try and commit to this vector without positions I in it, how would you go about it? Well, you would compute the RSA accumulator over all positions in N except I, right? So I'm going through all positions from 1 to N except the positions in I. And this is really like the accumulator S raised to 1 over EI, where S is the accumulator over all positions in N, right? Does everyone agree? So remember, S was...
EI is a vector of primes?
Good. So sorry, EI is just a product over all of the...
Okay.
Yeah.
That makes sense.
The animation never works out as I want it to. Right. So I have this RSA accumulator for this half vector now. And then I also have to compute its lambda component. And its lambda component, remember, has to be a membership witness with respect to the RSA accumulator of the vector's positions raised to the value at that position. And that's exactly what I have here. I have a witness for each J with respect to SI raised to its VJ, and I do a multi-exp. And that's by definition the digest of V without positions I in it. And that's actually a proof for the subvector. And the way you verify it is, well, you take this SI, you sort of add back the positions in I to this lambda I, and you check that you get back the original digest. I'm actually not going to go through the verification here, but you can see our paper for that. But the idea is that you can verify it in linear time, where linear in the number of positions in the I subvector. And really, the reason I'm explaining things this way is because I want to make you realize that a proof is really just like a digest. And because the digest is updatable, the proof is updatable too. Just like we can update a digest after something in the vector changes, we can update a proof too. Okay? And to give you an example, if J changed by delta J, then all I take is I take lambda I and I raise it and I multiply it by this guy raised to delta J, where this guy is the membership witness for J with respect to SI, and that kind of tweaks the VJ in here, right? And one observation I want to make is the question is like, if I'm doing this update, where do I get this thing from, this membership witness for J with respect to SI? Because if I'm doing the update, I have SI, but I don't have an EJ root of SI. However, I can ask the person who's giving me this update to also include this S to the 1 over EJ with the update. And if I have additionally this S1 to the EJ, I can actually compute a root, an EJ root of SI, which is really an EI times EJ root of S, using a so-called Shamir trick. And what a Shamir trick does is it takes an EI root and an EJ root, and it outputs an EI times EJ root. And I won't go into details about how it works. You can see our paper for that. You can see Campanelli's paper. It uses the extended Euclidean algorithm. It's a very useful trick in this line of work. So that's subvector proofs. The other cool thing about these vectors, as shown by Campanelli et al., is that you can actually extend them with new positions. So I can add a new position n+1 with value vn+1 to a vector v with n positions. And the way I can do that, well, it's very easy to update the accumulator part of the digest. All I take is the previous accumulator and I exponentiate it by this en+1 associated with position n+1. And now I have an accumulator over all positions from 1 to n+1, right? Does that make sense? And for the lambda part of the component.
Sorry to interrupt.
No, great.
Is there a limit? Is there a limit on the range of the values that in the dictionary?
Yes. So as I mentioned in the initial slide, the values have to be L-bit numbers, and the primes have to be greater than L+1 bit numbers.
I see. Okay.
For security to hold. Yeah. Right. So for the lambda part of the digest, well, lambda needs to have a witness for position n+1 raised to the value at position n+1, and that's what this guy is. But then I also need to update the previous witnesses in the old lambda to be with respect to this S+1, this S prime, by multiplying, by exponentiating with this En+1. And this might not be intuitive, so I'm just actually going to expand this equation to see why this holds. So if we expand this lambda, remember it's just the product of all positions from 1 to n of witness with respect to S, which is the old digest, raised to Vj. And now I'm raising all of this to the new En+1. And now I can actually do two things. The first thing I'm going to do is I'm going to rewrite S as S prime to the 1 over En+1, which I can do. That's by definition what S is. And then I'm going to move this En+1 inside this, this bracket here. And I know that S to the En+1 is S prime. So I get an S prime in here. And now if you look very carefully, I can actually just merge in this guy into the product, and I get the product over all J from 1 to n+1 of S prime, so membership witness with respect to the S prime for position J raised to Vj. And that's why I can add new positions to the vector. And I can actually repeat this, you know, so if I want to add several new positions, I can do this sequentially. I can take this new updated digest and add an n+2 position to it by just doing the same thing. Okay. And this is something, I'm not sure that we explained this in the paper. I think we touch upon it briefly, but it's actually quite useful in the next slide and in the rest of our construction. So next I want to tell you about how CFVCs disaggregate proofs. Again, we're still in the background section. We haven't gotten to the meat of the talk. So suppose I have a subvector proof for I, and I want to build a subvector proof for K, where K is a subset of I, right? So how can I do that? This is called disaggregation. I have a proof for a lot of things, and I want to get a proof for less of those things. Well, first, let's define this delta as the things that are in I, but are not in K. And notice that really what I'm trying to do is go from a digest of V without I in it to V without K in it, right? By definition, that's what a proof for I is, and that's what a proof for K is. And we can just notice intuitively that V, if I add V delta to V without I in it, well, what I actually get is I get V without I in it, and I can expand the deltas to, by definition, delta is I without K in it. And now these VIs cancel out. So actually what I get is V without K in it. So really all I need to do to get a subvector proof for K, where K is a subset of I, is just add back the things that are in delta to the proof for I. And I know how to add back things to a digest. I just told you here how I can add new things to a digest, right? So that's exactly what I'm going to do. For each I in delta, I will sequentially add it to Si and lambda I and get Sk and lambda K. And this will take me L times size of delta group operations, as shown in the previous slide. So in an earlier version of the talk, this was way more complicated, but I think this is actually the simplest way to do aggregation. And the nice thing about this is that you actually get a faster disaggregation protocol than the one proposed in CFG plus 20, as far as I can tell, unless I'm making some horrible mistake here. I did figure out this late at night, so it's possible that it's completely wrong. So please let me know if you find a bug. But it looks right to me. And an implication of this is that you can actually compute all proofs in n log n time rather than n log squared n time, which is what the original CFG paper proposed via disaggregation. Now, how do you compute all proofs via disaggregation? This is not intuitive, but the idea, well, it's actually intuitive, never mind. Take a proof for the full vector. Imagine you have a proof for the full vector. Disaggregate it into a proof for the left half and a proof for the right half. Then disaggregate it into a proof for the left, left, and left, right, right, left, and right, right. Continue all the way down until you get the individual proofs at the bottom, right? So this is a really beautiful algorithm by Campanelli et al. So disaggregation is actually quite a useful trick for computing proofs efficiently. And yeah, like I said before, they claim n log squared n, but I think if you do disaggregation in this faster way, you can get a faster algorithm. Okay, so we're almost done here. Another thing that CFVC support is incremental aggregation, which means I can take a proof for I and for J and obtain a proof for the union. But then if I get another set K, I can also continue this aggregation incrementally and get a proof for the union of I, J, and K. I'm just going to show you how to do the proof for I and J here. And I'm going to assume they don't intersect, because if they do, it's easy to disaggregate one of the proofs so that they don't intersect. So if I have a proof for 1, 2 and another for 2, 3, I can disaggregate the proof for 1, 2 into a proof for 1. So now I only need to aggregate the proof for 1 and the proof for 2, 3, right? So I don't need to worry about intersection. And again, the idea here is that I'm going from a digest of V without I and a digest of V without J to a digest without both I and J in it, right? And the first thing to notice here is that I can easily compute the accumulator part of the proof by, again, using a Shamir trick. So the accumulator part of the proof will be an EI EJ root of S. That's what the digest of V without I and J will look like. And this I can again do via a Shamir trick. I have an EI root, I have an EJ root. They're both in the pi I and pi J proofs, and I can get this EI EJ root. And yeah, and the other part is computing the lambda of pi I UJ. And this lambda is kind of a mouthful, so you have to do a product over all positions n without I union J in it, RSA witness with respect to SIUJ raised to the value at that position. And you can kind of rewrite this, like you can pull out the exponent from SIUJ in here and write this as S. And this will actually help you figure out how to compute the lambda IUJ. Basically, you tweak the lambda I into something that looks like this, and you tweak the lambda J into something that looks like this, and then you do a Shamir trick to take this root. Now, I'm not going to explain this in details because I think it's too complicated and we don't really use it in the rest of the talk. I do have it in the appendix if you want to discuss it at the end of the talk. And really, this just takes 2 root factors in a Shamir trick. And that's what I'm going to say. And I'm also going to say that it takes quasi-linear time to aggregate, assuming I is greater than J. So that kind of covers the background. So I hope you know you can gain a glimpse of how beautiful this construction is. And let me show you how you actually turn this into an authenticated dictionary. So suppose I have a dictionary D, I can basically treat it as a sparse vector. I can treat the keys as indices in a vector. And the digest of this dictionary will have the S and the lambda part as before. The S as before is just an accumulator over all the keys where I hash each key to its prime EK. And the lambda part as before is RSA witness for K with respect to S raised to VK product over all of these. So nothing changes here. The only thing that changes is I'm treating keys as indices. In fact, this is so obvious. Like I'm so pissed I didn't realize this earlier. You know, like I've been looking at this scheme for quite a while, and it's a very simple observation. And similar to Catalano-Fiore VCs, because we haven't changed much, the digest remains updatable. And I know I can add new things to the digest, as I showed you before, so I can easily add new keys to the dictionary. But I haven't shown you how to handle removing keys from the dictionary. So we'll do that. The proof for a bunch of keys K remains the digest of the dictionary without those keys in it, just like a proof for a subvector was a digest of the vector without those indices in it. And the proof remains updatable, except I have to handle removing keys from the dictionary once again. So how do I update a proof after a key was removed from the dictionary? And the proofs remain incrementally disaggregatable. And I want to say this is actually a concurrent idea with AR20, the ePrint that elegantly removes update keys by Shashank Agrawal and Srini Raghuraman. So I really encourage you to read their paper. They have a really beautiful way of removing these update keys. But what we do is we go in a slightly different direction. We add this new notion of cross-incremental aggregation, which I'm going to explain next. And we add support for non-membership proofs, and we add strong binding to the dictionary. So this so far is weak binding. And we add append-only proofs. And let's just first, I'm going to kind of treat all of these in order. How do I update the digest after adding or removing a key? Well, you know, as previously shown, if I add KVK, if I want to add KVK to the dictionary and get an updated digest D prime, I can basically use the trick for adding new positions to the vector. So I'm not going to go over that because I can add new positions to the vector. I can add new keys to the dictionary. The more interesting case is how do I remove things from the dictionary? So suppose I'm removing a key K hat with value VK hat from the dictionary. The thing to notice here is that the updated digest is the digest of D without DK hat in it. But by definition, this is actually the lookup proof for pi K hat with respect to the digest D. So remember, a lookup proof for an individual key is just the digest of the dictionary without that key in it. But that's also the updated digest of the dictionary after removing that key, right? So to update a proof, so to update the digest after removing one key, I just set the digest to be the proof for the removed key. So I need this as auxiliary information. And again, if you read the AR20 ePrint, you don't need this, which is really cool. But in our construction, you do. Now, what about multiple removals? Suppose I'm removing a bunch of keys in a capital K hat. Now I have a bunch of lookup proofs for each individual key in the set, or maybe I have an aggregated lookup proof for all of these keys in the set. Well, again, the thing to notice is that the updated digest is just the dictionary D without all of these keys K hat in it, but that's by definition the aggregated lookup proof pi K hat with respect to the old digest, right? So if I get individual proofs for all of these things in K, I can aggregate them into this pi K hat and I set the digest to be that, right? So that covers updating the digest after removals, after additions, and we know that we can update the digest after changing keys, just like we could update the vector commitment before. What about updating proofs? So again, a proof for K is just a digest of D without the keys K in it. And I know that after I add a key, I can update this proof in the same fashion as updating the digest. In the vector after adding new positions. So again, we're not going to go over that. Question is, how do I update? And I also know that I can update a proof after changing keys in the dictionary, just like I could update the vector. So again, the question remains, how do I update this proof pi K to a pi K prime after removing a key K hat, VK hat from the dictionary? And importantly, so this new proof pi K hat has to verify with respect to this new dictionary D prime that doesn't have this key in it. So D prime is D without that key in it. And the thing to notice here is that, by definition, pi K prime is the digest D prime without the keys K in it, right? Without the keys K in it, right? That's by definition what a proof of K is. And I can rewrite this. So I can expand D prime. I know D prime is D without DK hat. So I put this here. and d prime k stays the same. But then I noticed that d prime k is actually the same as dk. And now what I notice is that, well, this updated proof pi k hat is just the digest d without k hat and without k in it, which by definition is the aggregated proof for k and k hat, right? So if I want to update a proof, I just, after removing a k hat, I just aggregate that proof with k hat. That's the intuition here. And that kind of covers proof updates. So we talked updating digest, updating proofs. And remember, these proofs are aggregated, right? So they're proofs for a bunch of different keys. Let's move on to the more interesting part, which is the cross-incremental proof disaggregation. So again, I have a bunch of different dictionaries, DI, M of them, and I'm gonna change notation a little bit. I can no longer use S and lambda because of these I subscripts. So digest of DI will be AI and CI, where AI is the RSA accumulator over all keys in the dictionary. And CI is the lambda part, which is RSA witness with respect to AI for K raised to the value at K. Now, a proof for a bunch of keys, KI, with respect to its digest DI, I have a bunch of these proofs. So I have M different proofs, each with respect to a different DI, will be this EKI truth of the RSA accumulator AI by definition. So I'm going to call this WI. Again, I'm changing notation. So previously this would have been S and this would have been S sub K. But now, because I have a bunch of different proofs, I'm using this new notation. But all that I want to say is that this is just an EKI truth of the RSA accumulator in the digest, because that's basically an RSA accumulator over all keys in DI except the keys KI. And then there's the lambda I part of the digest, which I'm rewriting slightly differently here. So the RSA witness for K with respect to WI is AI raised to 1 over EK raised to 1 over EKI, because AI raised to 1 over EKI is WI. And if you take an EK root of that, you get a witness for K with respect to WI. This is a bit of a lot to process. So all I'm saying is that the witness is this raised to this, and I'm raising all of it to VK, right? So you can move this guy inside here, and that's the witness with respect to WI. So again, this is just a proof for KI. And I'm gonna play with this a little bit. I'm gonna rewrite it as, I'm gonna take this difference here and I'm gonna write it as a fraction. So here I have the product over all keys in the dictionary, and here I have the product over the keys in KI. And right, so far so good. And this guy stays the same here. And then I noticed that, well, this thing at the top is actually just CI by definition, right? So just look here, this is just CI. And this guy, I'm gonna leave it unchanged, except I'm changing the notation from DKI to KI, which is basically the same. And I'm gonna baptize this guy as alpha I, and that's that. And what I wanna point out here is that a proof for KI consists of an EKI truth of something and an EKI truth of something else. And in general, all of these different proofs for these different KIs will be an EKI truth of something. And Bonnet et al. Give a protocol for aggregating such co-prime roots. So if I have a bunch of roots, of co-prime roots EKI, with respect to different things, I can actually aggregate them very simply by doing a product over them. Similarly, here I have a bunch of EKI roots of these AIs, and I can also aggregate them by doing a product. But there's a caveat. The scope primeness is the caveat. So I can only do this aggregation if the EKIs are co-prime. But it turns out they're not co-prime. Let me tell you why. So again, they have to be co-prime for this aggregation to work. So the GCD of EKI and EKJ has to be 1 for all I different than J. But this is not true, because I could have the same key K within different KI and KJ. And that means that EK divides this EKI and EK divides this EKJ. And their GCD will be at least divisible by EK or greater than that. So these things are not actually co-prime. So that's kind of a bummer. How do we aggregate this if they're not co-prime? And we kind of hack our way around this. What we say is, we require a different hash function, hi, for each dictionary di. So this EKI will hash k with hi rather than h. So ki will have hi of k, and kj will have hj of k. Therefore, you won't have the same prime dividing both of them, right? So this way, hi of k is different than hj of k, and their GCD remains 1, because if you have keys in common, they'll hash different primes. But of course, this is kind of a limitation.
Do the different hash functions need to hash to disjoint sets of primes?
Well, I think the only property you need is, given a key k, hi of k should be different than hj of k. Disjointness would totally give you that. I'm not sure that you need to be fully disjoint. Like you could have the hi of k1 be some prime e, and actually, no, you're right. No, you can't have that either. Yes, good. So they need to be disjoint.
Okay.
Yes.
Can't you just use like pre-image resistance here, right? If it's hard to find a pre-image, we're not going to be able to find something which, or any rate sort of cross-collision resistance. So they don't have to be disjoint. They just has to be hard to find a solution.
Yeah,
well, I'm not sure that's correct, because the GCD will not be equal to 1.
So these are not primes.
Any collision.
The E sub ki are not prime. They're products of primes. They contain primes in.
Right. But is the hi of k prime? Because if so, then all you need is some sort of cross-collision resistance.
Yes, the hi is prime.
Okay.
Yes, the output of the hi's are prime. Yeah, so you need cross-collision resistance, which you can easily get if you consider, like you take h and you prefix I into h as input, because h is collision resistant, hi and hj should be cross-collision resistant.
Right, but they don't need to be provably disjoint. They just need to. You just need to have a hash with a large enough output set. Okay.
Mm-hmm.
Yeah.
But again, I want to say this is kind of a limitation, because we require the dictionaries that we do the cross aggregation for to use different public parameters. So each DI has to have its own hash function hi that the prime representatives are computed with. And this is not ideal. Ideally, we would like to aggregate proofs across dictionaries with the same public parameters. And we leave that as future work.
Can you not just remove the keys that are going to collide first, from the same way that you did earlier with when you
were, well, but you can't, because you want to prove that those keys are in ki. I want to prove that k is both in ki and k is both in kj. You know, I need to make that statement about the key k being.
Oh, yeah, I guess. Yeah, okay.
I can't really disaggregate my way out of this. Okay, so for the verification, I'm going to define, this is how Bonnet et al. Show how to verify such a POKCR aggregated proof. So I have this E star, which is the product over all of these EKIs. So remember, the EKIs in turn are product over a bunch of primes for each key in KI. And I'm going to define this E star in this way. And to verify that, I want to verify that each WI is an EKI root of AI. And I want to do this for all WIs, but I've aggregated them within W. So how can I do this? Well, Bonnet et al. Show that it's sufficient to check this equality holds. And I won't explain why this works. But intuitively, you can sort of mask out the E here, the E star here, and notice that this really checks that W was computed correctly from the WIs. But it's not as simple as that, because if you check it in this way, which you can do very fast via this algorithm that Bonnet et al. Introduced called multi-root X, if you check it in this way, then you can actually extract all of the WIs from W. So it gives you a really strong property. So I can actually recover the WIs from W if this holds. And one of our contributions is that we give a faster algorithm for this extraction that saves a factor of order n by log n work. And we actually need to extract these W's after doing this verification, because we need the WIs to apply a few root factors to it, so we can reconstruct the alpha i's against which were defined in this way, against which we verify the lambda i's that are aggregated within lambda. So remember, the lambda I is an EKI truth of alpha I. And to verify all of the aggregated lambda i's, I do the same type of verification where I compute this right-hand side using multi-root exp. Again, I'm not going to give details about this, but this is in the Bonnet paper, and we also explain it in our paper again. And you know, I don't have a good way to explain this yet beyond the fact that if you understand how you can extract all of the WIs, if this holds, then you should see how this equation actually checks that each WI is equal to EKI truth of AI. So you can see our paper for that. You can also see the preliminaries of our paper. I do want to say that if you read Bonnet's paper, there's some typo in their algorithm for extracting the WIs from W. So please be mindful of that. At least in the ePrint, I believe there's a typo. I don't know if in the crypto paper is. So in our paper, there's no typo as far as I can tell. that might be clear. Okay, so we can verify the cross-aggregated proof. And if B is the max size of a KI, then the verification can be done in sort of quasi-linear time in the number of cross-aggregated proof and in the size of each aggregated proof. So this basically comes, this is the time to do the extraction of the WIs, this part, and this log B part is the time to do the root factors, which I didn't go into details about. And you can see more details about this in our paper. I'm not gonna bore you with the math. A really cool consequence.
So, sorry, what was B again?
Oh, B is the max size of a KI. So remember, I have a bunch of KIs.
Oh, sorry, yes.
Cross-aggregating. Yeah.
Got it.
Oh, so we're almost running out of time. One quick thing, and I'm actually done. So one quick thing I want to say is that because I can extract the individual aggregated proofs from the cross-aggregated proof, this actually means that I can disaggregate cross-aggregated proofs, which is kind of neat, but it also means I can update them because I can disaggregate them first, then update the original aggregated proofs, and then re-aggregate them. And perhaps there's a way to do this faster than that, but at least in principle, I can update cross-aggregated proofs. And that concludes the UAD part of the presentation. And real quickly, I want to go about other things that we add for applications beyond stateless validation. So I mentioned strong binding for our AAD construction. And the idea for providing strong binding is that you have to make the security proof work out. And if you try really hard to make the security proof work out, you all of a sudden realize that if in addition to this SK lambda K part of the proof, you also include a non-membership witness for K with respect to SK, which is actually just yet another RSA accumulator, that totally makes the security proof pass. Because you can use this to do some GCDs and get a strong RSA break. So I don't have a lot of intuition to give here beyond read the security proof and see how this helps. But because I've added this RSA non-membership witness to a proof, I now downgrade to one hop aggregation because RSA non-membership witnesses, as far as we know, are not incrementally cross-aggregatable because POKey proofs are not incrementally aggregatable. They kind of are aggregatable, but they're not linear. They're not constant sized after you aggregate them. You have some integers left over. We also add non-membership proofs, and this is easy to see because if I want to prove that a key is not in the dictionary D with digest S lambda, all I have to show is that key is not this in the key K is not in this RSA accumulator S, right? And I can do that using an RSA non-membership witness with respect to S. Finally, append-only proofs. Suppose I have an old digest for dictionary D and the new digest for D prime. Well, the one thing I have to observe is that the S prime in the new digest is actually S raised to some integer U, and the lambda prime in the new digest is lambda raised to that same U times S raised to some integer Z. And it turns out that if I show this holds, I can prove append-only security holds. I can prove nothing has been removed from the dictionary, only new keys have been added. And we formalize this in the paper and we prove security in the appendix. And that's kind of, yeah.
When you say new keys have been added, that means no existing keys have been changed.
Yes, well, exactly. Yeah, only new keys have been added. Yes.
Got it.
Yes. Okay, so I'm ready to conclude now. So it seems to me that these CFVCs just keep on giving. So they're a really beautiful construction. We showed how to get cross-incremental aggregation for dictionaries with different parameters. It'd be really nice to do it for dictionaries with the same parameters. We showed how to get authenticated dictionaries with strong key binding for applications like transparency logs. And for that, we also need these append-only proofs. And we showed how to add non-membership proofs to our authenticated dictionary. And again, I want to encourage you to read the ePrint by Shashank Agrawal and Srini Raghuraman for how to remove update keys. I think they have a really beautiful idea there. And really, the open question is, what else can we do with these VCs? They seem to be really powerful, really cool. So that's how I'm going to end this talk. And I thank you for your time and attention. And if you want to discuss more, I'll be here. Thank you.
Thanks, Alin.
Look at that,
We
1 hour sharp.
Yeah, so we have 30 minutes left to discuss the paper and for anyone who wants to ask any questions. So with that, please, anyone feel free and step in.
Also, I've muted all of you, so you would need to unmute yourself if you want to ask anything. I guess a lot of people are thinking.
So I guess one question is about concrete efficiency.
Good.
So suppose we're using RSA. That means, I guess, that it has to be an RSA for which we don't know the factors.
Order.
Is that right?
That's correct. So we need a trusted setup.
Right. Okay.
But it's a simpler setup than a QSDH, let's say, setup where you have this huge CRS.
Sorry, I can't remember what the MPC-based setups for RSA groups look like. Does the modulus have to be larger than it normally would be?
No.
Okay.
Okay.
I think
so
there's
let's say we're.
Are there any smoothness constraints? Sorry, apologies. Go ahead.
I think there's a thing where you can do an unstructured setup, just take a random number. It just has to be absolutely huge.
Oh, okay.
Yeah. That's in principle, yes, but in practice, no.
Okay.
Okay, so let's say that we're using, I don't know, 3096-bit RSA. So let's look at the costs of the particular algorithms.
So I guess one thing you're going to be interested in is how long does it take to compute all proofs? How big are the proofs? So proofs are 2 group elements, whether they're individual lookup proofs or aggregated lookup proofs or cross-aggregated lookup proofs, just 2 group elements. The time to verify, for example, one thing that will be of concern is this time to verify. You know, it's conceivable that you cannot do faster than B times M because you have B times M keys that you need to go through to verify the proof, right? But this L factor is inherent from the L bit size of the primes. This log squared M factor would be nice to get rid of. This log B factor would be nice to get rid of. But in principle, you shouldn't be able to do faster than order BM to verify a cross-aggregated proof. To verify an individual proof for B keys, an aggregated proof for B keys, I think it's just order LB time. I could be wrong. Do you need to do root factors to? Maybe it might be order LB log B time actually, because you might need to do a root factor. But no, is that true? No, you just add back the keys. No, you should be able to do it in order LB time. I take that back because you can just add back the keys to the proof and make sure you get the original digest by adding back the keys to the proof, because the proof is just digest without keys. You add the keys back to the proof, you get the original digest, and you can add the keys in order LB time.
So by a G question mark ops, that's multiplication in the RSA group. Right?
Yes, good. Yeah, I didn't want to say exponentiations because this seems more precise. But you could shave off this L factor, which tends to be 256 bits anyway. It's like a security parameter, and you could change this to exponentiations. So then you have order BM, hidden order group of size, exponentiations of size L.
Huh. That seems as though it could be quite practical?
Yes, I don't think it's, obviously pairing-based stuff will always be faster, but it's not out of the realm of possibility. The more concerning stuff, I think, is the size of the proofs. But when you consider cross-aggregation, like imagine a stateless cryptocurrency, you have a bunch of smart contracts. You're proving things about the reads in the memory of the smart contracts. So you're proving, let's say, thousands and thousands of reads, and now you're cross-aggregating all of this proof into 6,000 bits, right? Let's say. That's pretty nice. You have to send the keys anyway and the values of those keys, and the proof overhead is really small. Now, the time to verify is gonna, not be super fast, but who knows?
I don't know, maybe you can just use a snark and arrange for the arithmetic to be fast in the snark, and then the proving will be expensive, but the verification won't be.
Right. Yeah. I also want to say that, this cross-aggregation requirement for each DI to use different public parameters is actually not a problem in the smart contract setting, as far as I can tell, because each smart contract can easily use its own hash function HI to compute its authenticated dictionary. But for other applications, it might be.
Oh, I see. So basically, if your system has lots of independent things that don't interact very much with each other, then it's going to be easy to do this cross-aggregation. Okay.
Anish, I think Anish, you had a question as well. Would you like to ask?
Oh no, I was just about to ask. Given there was all this question about size of primes, I was wondering if there was any smoothness requirement, because you are doing a lot of GCDs and things like that. So security margin could be much lesser if you have some smoothness requirement.
Sorry, I didn't quite hear what you said there.
I said if you are doing a lot of GCDs, especially in RSA, they might have. I was wondering if there was any smoothness requirement. So number of factors in that sense, and what the size would be, the largest one in that sense.
Number of factors in what?
In the size of the largest factor in that sense, that's a smoothness. So when you do factoring,
so you're talking about the RSA modulus N, if there's any smoothness requirements on N.
That's a smooth. Yeah, absolutely, yes, yeah.
So actually, there's like a great Stack Exchange question right now about the security requirements of on N for RSA accumulators. I think it's still unanswered.
Okay.
But yeah, all I can say is I'm not a crypto analyst, so all I can do is prove this is secure as long as strong RSA holds in the group. Now, what does it need for strong RSA to hold in the group? I don't know. That's, obviously you need to pick N randomly as a product of two primes.
Yeah.
You probably need to operate within a subgroup of quadratic residues. But beyond that, I'm not sure what to say. So I think other people are better suited to answer that question than I am.
I just posted the link to that in the chat.
Oh, great.
Okay, thank
it's
you.
The right question.
Yeah, yes. So criteria for public modulus of RSA accumulator. So that's in some sense what you're asking, Anish, because if you think about the CF scheme, it heavily relies upon RSA accumulators. So it definitely needs security for RSA accumulators to hold. It might need some other things. Well, it seems to just need strong RSA. And in fact, you can even get rid of strong RSA and reduce to RSA for weak binding, I think. Yeah, so sorry, I don't have a better answer to your question.
No, sorry. I was just thinking out loud, because you're using a bunch of GCDs, and what that has to do, in terms of security, has significant implications of the size of your factors in that sense. And also, when you were talking about speeding it up, so depending on the smoothness, you can have some speed as possible. So that's kind of when it went to my head, when you guys started thinking about what the size and how fast you could run.
Okay.
Thank you.
Aren't we always taking GCDs of products of large primes?
We're taking, I mean, we need certain GCDs to hold between these products of large primes. For example, here, GCD is one between these prime representative products. We're also taking GCDs when we're doing Shamir tricks, like for example, when I aggregate a proof, like here, I have to do a Shamir trick to aggregate the RSA accumulators. I think that comes up, well, it's much earlier in the talk. Where else do GCDs turn out? Disaggregation, we don't need to do GCDs. I think it's when aggregating and when, yeah, just when aggregating.
So what are the requirements on the hash function?
The hash function
Does it just
H,
have to return H, yeah?
yes, has to output L+1 bit numbers, has to be collision resistant. Now, I think collision resistant is actually needed just for correctness, not for security.
I see, okay.
So
it doesn't have to be a random oracle, it just has to produce distinct primes.
Yeah, I want to say so. So, for example, in POKCR, we need collision resistant for correctness. If we don't have a collision resistance here, we cannot aggregate, right? In the security proof, I never need to assume that the primes are different. I need to assume things about GCDs. Yeah, I should revisit that more carefully. My impression is that the collision resistance is needed just for correctness and not for security. Could be wrong. Yeah.
Okay, thanks.
Following up on that question, so you mentioned that the requirement to have a different hash function as public parameters for each dictionary is one potential limitation in an area that this could be extended. What other areas are promising future directions, do you think, for this line of research?
Let's go. Can we go? Let me see if I can go to the. I can't easily navigate this damn thing. It's so big. I wanted to go to the table.
I had that problem with my talk.
How can I? Let me. Okay, I think I've stopped screen sharing. I'm going to preview this differently with the page numbers. Come on, Text Studio, work with me. Okay, and now we can start screen sharing again. Text Studio. Let's. Where are you? Where are you? Where are you? There you are. Share. Let's go to page. What? So to answer that question, I would just wanted to look at this table. So, I think what one important direction is to get rid of these update hints. So for example, the KVAC construction by AR20 is arguably a better fit for stateless validation because they don't need update hints, which can be kind of problematic. Now, I haven't given it too much thought as to how problematic they are, but this is a big plus. On the other hand, they don't have cross-incremental proof aggregation. So when you think about different smart contracts, you can't really cross-aggregate the proofs. So that's kind of a bummer and it will result in a bigger proof size. So I would say, we want something that's cross-incremental and update hint free. That would be really cool to get. Also, as touched upon Dara, it would be nice to have something more concretely efficient, like from bilinear pairings, for example. Now, incremental aggregation from bilinear pairings doesn't really work out. I think that's an open problem. So this partial fraction decomposition that is used to aggregate proofs in bilinear things, as far as I can tell, can't be incrementally applied because the polynomials don't work out anymore. But in principle, so a subvector proof in a KZGVC is just a polynomial commitment, and you're going from a polynomial commitment of some degree to to polynomial commitment of a smaller degree. So that in principle should be possible. You're not going from small to bigger, which might break some assumptions. So
when I've looked at bilinear accumulators, they've all seemed to have reference strings that are the linear in the maximum number of elements.
yes.
Is that the case? Okay.
Yes.
And that has kind of put me off thinking about how to use them, because in the protocols I'm interested in, that's a showstopper.
Yes, well, actually, so for example, for bilinear accumulators and vector commitments, both have linear size parameters, but for the stateless setting, those linear parameters are only problematic during the setup, in the sense that you have to do this large setup. But once you do it, in the protocol, you never have to deal with their linearity. In the protocol, each user, for example, only stores their constant size update key. The miners only store constant size things. There's the proof serving nodes, which compute all proofs which need the linear public parameters. So I guess that's slightly, there's an asterisk there. There are some entities that deal with them, but they're not as problematic as one might think. But yes, I agree with you. They are a pain in the butt. Yeah. Yeah. So I think Alex, to answer your question, the first thing that I think of is, can we get cross-incremental and update hint freeness? For the AAD, updating the AAD proofs might be useful for the certificate transparency setting, where each web server has their proof with respect to the log, and as new things get added to the log, they need to update that proof. And update hints might be annoying in that setting too. Yeah, so I think even cross-incremental aggregation for AADs might be useful. Oh, something is beeping. Because you might imagine a world where you have a bunch of transparency logs. You might have a certificate transparency log. You might have a software transparency log. You might have a, machine learning data transparency log. And you might have programs that talk to all of these things, and cross-aggregating proofs across these logs might be important. So even here, can we get strong binding and cross-incrementality? That would be nice.
So does that have to reduce, do you have to, I guess, then solve the underlying problem of the hash? Because if you introduce the hash function, then you need to, is that limiting you from going to strong binding versus weak binding, or is that an unrelated problem?
No, the hash function is unrelated to the weak and strong binding. For AADs, if we could get cross-incrementality even across dictionaries with different parameters, that would be okay too, because the logs could conceivably have different public parameters. It wouldn't be that big of a problem. And it's not like you need to rerun the trusted setup. The public parameters only differ in the hash function, not in the modulus n. So that would be okay. But yeah, I think it's quite open. It's if you look at this table, there's only 1, 2, 3, 4, 5, 6 authenticated dictionaries from non-Merkle assumptions that I could find in the literature. So there's not a lot of work on this. You clearly get more power from algebraic constructions. What else can you do? We need to find out.
Cool.
Thanks, Alin. How anyone else have any more questions about the paper or any related kind of topics?
And I'd say if not, then I think we could probably wrap up, unless, Alin, unless you want to say anything else.
No, nothing beyond. Thank you for your time, attention, questions, and feel free to reach out if you want to collaborate on RSA things or bilinear things, or and cool. Yeah, thanks for coming.
Thanks so much for doing the study club, and thanks to everybody for joining.
And thank you again, Anna, for having me, and Alex for organizing.
Totally. I think you both need to stop your recordings when you have a chance.
All right.